Section 13.2, conduction. This is the second of our heat transfer mechanisms. We just saw convection, now we're on to conduction. Conduction is the process where heat is transferred directly through a material with any bulk motion of the material playing no role in the transfer. So this is where we have to go through the material. One mechanism for conduction occurs when the atoms or molecules in the hotter part of the material vibrate or move with greater energy than those in the cooler part, right? So if the molecules are moving slower, if there are collisions between the hotter ones and the cooler ones, then the more energetic molecules can pass their energy to the less energetic neighbors. So that's one method of how conduction actually works. It's the sort of thing that you can study more in material science or chemistry. We're just dipping our toes into it right now. And we'd say that materials that conduct heat well, we call them thermal conductors, and those that conduct heat poorly are thermal insulators. So that's the basis here, right? Thermal insulators, things where you don't feel that heat transfer as much. Great illustration of this is if you're out camping in, say, Canada in the winter. You need to go use the restroom and there's only an outhouse, and there's a choice of two toilet seats. One is made of wood and one is made of aluminum. Which one do you choose? You definitely want the wood one if you're going to have to sit down, right? Why? They're both the same temperature. It's not that the aluminum one is actually colder, but it's a much better thermal conductor. So it will conduct your heat away from your body much more quickly than the wooden one. So the material definitely makes a difference in the conduction. What else makes a difference here? Well, the amount of heat that is conducted through something like this bar, which we can imagine is a good metal chunk, is going to depend on a number of factors. One, the time during which the conduction takes place, right? If you've ever burned yourself cooking, you'll know it makes a difference how long you're in contact with that hot surface versus if it's just a really short duration. Also, the temperature difference. If there's a larger temperature difference, you're going to get more heat flow through. Similarly, the cross-sectional area of the bar. If it's a larger cross-sectional area, then you'll get more heat flow, right? You get more heat when you stick your full hand on the burning pan, or the pan isn't burning, the hot pan, versus if you stick just your fingertip. I don't recommend either, for the record. I'm just really talented at burning myself by accident. And then also the length of the bar, where the length of the bar will actually reduce the amount of heat passing through, right? If you have, for instance, a poker, something you stick into the fire, then it helps, or a spatula, it helps for it to be longer, because the longer it is, the further that heat has to travel to go from one end to the other. So all of these ideas are wrapped up into an equation that describes conduction. So the conduction of heat through a material is given by this equation for Q. The amount of heat conducted during some time t through a bar of length L, cross-sectional area A, is blank, right? The amount of heat is K, which we'll get to in a moment, times A, that cross-sectional area, times the difference in temperature, times time. Notice we have two different t variables here, but they are very different, divided by the length that it must pass through. K is the thermal conductivity. That tells us about the material itself, how good it is able to conduct the heat. What are the units of this thermal conductivity? Well, we could figure them out from everything else here. There is a number of things there, so let's just peek. So it is going to come from joules, our unit of heat, because heat is energy. So it's joules. And then per second from the time, per Celsius degree from the change in temperature, and per meter if we divide the meter squared by the meters in the length. So that is our standard unit for thermal conductivity. And thermal conductivity is something that's either given in the problem, or they tell you the material in the problem, and then you can look it up in a table. right? So here's a nice table of thermal conductivities of some selected materials. We have aluminum, which is very high thermal conductivity, versus steel is much lower. Gases are thermal conductors, but significantly lower than solids. And then we have some other materials, right? Asbestos, I can't say that, asbestos, there we go, is a really low thermal conductivity, which is why it was used in buildings for a long time until we realized that it wasn't so good for people's health. Body fat, also a nice thermal insulator. Concrete, diamond, some nice ones in here. Goose down, that's a good insulator, right? Styrofoam is another good insulator, which is why it's often used in cups. So this hopefully gives you some idea of the different thermal conductivities that you could have. Now, materials that have these dead air spaces or trapped air spaces are usually excellent thermal conductors, or thermal insulators, excuse me. Why is that? Well, by having all of these air gaps, like what you'd have in styrofoam, there's lots of little pockets of air, or in a down jacket, there's lots of little pockets of air. By making those pockets tiny, there can only be tiny convection currents inside. And air is a good insulator. So the heat would have to travel through the solid material and through the air, and then the solid material, the air. And so that ends up adding great insulation. If it's just wide open, you can set up some nice convection currents, or not so nice if you want to stay warm. And so it ends up not being a very good insulator. But by having small dead air spaces, you can have great insulation. And insulation is something that comes up quite a bit when you're trying to uh, build a house. So that's a common example here, layered insulation. One wall of a house consists of plywood backed by an insulation. The thermal conductivities of the insulation and plywood are respectively 0.030, 0.080 joules per second per meter per Celsius degrees. And the area of the wall is 35 meters squared. Find the amount of heat conducted through the wall in 1 hour. Right, so we want to know how much heat will go from the inside to the outside. In other words, how much heat are we going to lose just due to this insulation? So as we're thinking about this, one thing that's really important to note is first what's given, right? We have our thermal conductivities, our K values given, so we don't have to look in the table. They also give us the area of the wall. What else? Well, notice they have some more information packed into here. They have the thickness of the insulation and the thickness of the plywood, which we notice the plywood is much thinner than that of the insulation. What variable do we think that thickness is going to correspond to? Well, if the heat is flowing through the wall, that's going to be the length that the heat must conduct through. So we have a length of the insulation and a length of the plywood. We also have some temperatures given, right? Notice inside, our temperature is nice and warm, versus outside, it is much colder. Call it T out maybe. So that's all well and good, but because we have two materials, this is a little more complicated, right? Each of those materials has its own thermal conductivity and its own thickness. So it becomes a little bit harder to add them together, in part because each one has a different delta T as well. Our delta T is not going to be for the entire wall. We have to focus on one material at a time. So our delta T is not 25 minus 4, it's 25 minus whatever this interface temperature is, the temperature between those two parts of the wall. For the insulation, for the plywood, the temperature difference is the interface temperature and the outside temperature, right? So we have to consider this interface is a really key detail. We're going to have to look at the insulation separate of the plywood. One thing is our connection between both of them though, and that's that we have the steady heat flow. Because this heat flow is steady, it ends up that it is just like our heat gained is equal to heat loss. The amount of heat that flows through the insulation, Qi, is going to have to be equal to the amount of heat that flows through the plywood. They have to have the same value, right? So for however much the plywood gains heat from the insulation, you could say, loses the same amount of heat to the plywood. So that's one reference point here. And then we can use our conduction equation to actually figure out what is this interface temperature so that we can figure out the net heat flow through. So let's take a look at this. All right, so because the heat flow is equal to the amount of heat passing through the insulation as well as the heat passing through the plywood, we can set these equal to each other. So all of the quantities for the insulation heat conducted are equal to those of the plywood conducted. So notice we have the thermal conductivity of insulation, 0.03, times the area, which we know that area is 35 square meters. But conveniently, that same area is there for the plywood, right? They have the same area even if they have different thicknesses. All right, and then also we have the difference in temperature, which for the insulation is 25 minus the interface temperature, T, cool, times the time over which this happens. And notice the time is also going to be the same for both. So that time is the same as this time. We can plug in whatever time it was given. I think it was 1 hour. But if they're both the same, that's not critical. We know that that's going to cancel out. We can divide both sides by T and it will go away. And then divided by the thickness of the insulation, 0.076 meters. Similarly for the plywood, we have its thermal conductivity, 0.08, divided by its thickness, 0.019 meters. And so, like as I mentioned, the areas are going to cancel out, and we can also divide out the times. So those will disappear, and all that we'll be left with is a little bit of algebra to solve for T, right? So we can do that if we, at this point, we can just work with numbers and we get all the capital T's to the same side and divide everything else, subtract or divide everything else to the other side. If you do that, you should find that the interface temperature is 5.8 degrees Celsius. Notice, since it's 5.8 degrees Celsius, that's almost the same temperature as the outside. So the plywood is not doing much in terms of insulation. It's less than 2 degrees difference in terms of warmth. And the insulation is providing almost 20, no, not quite, 15 degrees difference, right? So it's doing the lion's share of the work here. And that's why we install insulation in houses. Not so much because it's a way better thermal conductivity, because the thermal conductivity, it is better, right? But even more so, it's something that we can make a thick amount of it. And so it can absorb a lot of the heat. Once we know this interface temperature, going back to the problem, we can figure out the heat passing through by using either of these, either Q insulation or Q plywood. And so regardless of which one you want to use, doesn't matter which, as long as you keep your signs correct, you can then solve for the total heat that passes through. So let's take a look. So if you use the insulation, we have the 0.03 times the area. Now we need that area, the 35 meters squared, times the difference in temperature, right? Higher minus lower, so 25 minus 5.8, times the time. And notice, in order to cancel with the K value, which has units of seconds, we need our time to be in seconds as well. So we can't just plug in 1 hour because the units won't cancel properly. We have to remember, okay, in 1 hour, there's 3,600 seconds. So I'm going to write 1 hour as 3,600 seconds. And then divided by the length or the thickness of the insulation. And that gives us our total, sorry about that, the total heat that is passed through. That it is 9.5 times 10 to the 5th joules, because it is once again energy. All right, one more example to think about. Conceptual example now. If you have an iced up refrigerator, in a refrigerator, the heat is removed by a cold refrigerant fluid that circulates within a tubular space embedded within a metal plate. Decide whether the plate should be made from aluminum or stainless steel, and whether the arrangement works better or worse when it becomes coated with a layer of ice. So I want you to think about this, come up with an answer, and then move on the video. So go ahead and pause now. Right, did you do it? Okay. Well, if we think about aluminum versus stainless steel, that's going to go back to the thermal conductivities that we saw listed in table 13.1. And if you go back and check, you'll see that aluminum has a K that's 10 times bigger than that of stainless steel. So it is much, much bigger than that of the steel. As a result, it's going to be more thermally conductive. I highly recommend the aluminum because we want to conduct heat out of the refrigerator. We want to cool the refrigerator down. Similarly, when we add the ice, when it becomes iced up, that just adds another layer of insulation for the heat to pass through, as shown down here. So that's going to be less efficient as well. In this case, we want heat to flow because we want to cool the refrigerator down. So this is going to be a case where we want the aluminum plate without the ice. All right. Hopefully that makes sense to you. I would love to discuss it further. If you have any questions or comments, please send them my way. Let's figure this out.